Hi guys, I want us today to look at nonlinear regression. And when we talk about nonlinear regression, we talk about regression, which is not in the form of a straight line. In our previous classes, we have looked at simple linear regression, multiple linear regression, and all those equations are represented by straight lines, either in two dimension or in a multi-dimensional space. Now, today, I want us to look at nonlinear regression, and specifically, I want us to look at cases where we have quadratic terms in the explanatory variables. So, for instance, I want us to the model, consider the model y is equal to beta naught plus beta 1 of x plus beta 2 of x squared plus the error term. So that's an example of what we're calling nonlinear regression, which has a quadratic term. So this is what we are calling the quadratic term in this model, quadratic term. Quadratic term. But it's good for you to note that if you are fitting a model in the actual sense, if you're fitting a model, you usually don't start with a quadratic model unless there is strong indication that the relationship between the variables is quadratic. And the relationship can quickly be obtained using a scatter plot. If you put y and x there, then you notice that this is your scatter plot. There's some curved relationship like that. And that's a suggestion that if you attempt fitting a straight line, it will not be a very good fit. If you attempt fitting a straight line, it will not be a very good fit. So that is one thing that can suggest that maybe a quadratic relationship is better. Some of the curvatures, this is what we're calling a curvature. Some of the curvatures may be too small to notice. So you may end up starting with a linear model. So you just start with a linear model. Then when you plot the errors, you check the behavior of the residues. Then that can suggest either a quadratic model or maybe a higher kind of model. So in this model, what I want us to focus on is the interpretation of the regression coefficients. The interpretation of coefficients of a straight line usually is straightforward. Even in cases when we have log level models, or we have level log models, or we have log models, the interpretation is not very difficult, because you saw that if you have a log model, then the kind of interpretation we talk about here is in the elasticity, which is a common term in economic data. Then when you have log level, we talk about the percentage. So that's the difference between these two. And you find that these interpretations are simple and straightforward. Now, when you come to quadratic models, the interpretation of the regression coefficients beta 1 and beta 2 is not straightforward. We not just, in short, beta 1 and beta 2 are not slope coefficients. So we note that beta 1 is not a slope coefficient. Is not a slope coefficient. So that's a caution that is not a slope coefficient. That is, does not give the estimated change in y for a unit increase. Does not give that for unit increase in x. Okay, does not. Okay, so if you want to know the slope of that line, you consider the following model. So we say that to see, or to get, in order to get the slope of the fitted regression model, regression line, let me call it line, which is given by this y estimate is equal to beta naught estimate plus beta 1, like that. We use differentiation. Differentiation. In other words, we find derivative of this function. we find the derivative of that function. And that derivative function, will give you the slope for given values of x. We use that concept of differentiation. Okay, and how do we do that? Remember, differentiation is a concept that I think you have come across many times. So for instance, if a given y is equal to 2 plus 3x, then the derivative dy dx is equal to the derivative of a constant is 0, and then so this is 0 plus the derivative of this is 3. In short, the derivative of this line here is equal to 3, and we are saying that the first derivative is always the slope, and that agrees with what we know about this. This is a straight line where this is where it cuts this is the y-intercept, and this is the slope. So you see that this is the same as this. Okay, so even when you have higher order, like y is equal to 2 plus 3x plus x squared, so if you want to find the slope of this line, it will be dy dx, which is equal to, this will be 0 plus this will be 3, and then this will be 2x. So the slope of this quadratic function here, or equation, will be 3 plus 2x. And you can only find the actual slope if you are given x. If you are given x for given value of x. And that tells you that the slope is not the same. The slope is not the same if you have a higher order like this. It will be changing. And that explains why if you plot the quadratic curve, maybe it will look like that. So you find that you only get the slope of this function at a given point. So you don't have one value for the slope. This is your y, this is your x. So you'll be getting the slope for a given point, and the slope will just be the tangent to that curve at that point. So you find that every point will have its own slope like that, and that can be noted here. For different values of x, the slope will be different, and that is what we are seeing here. Like that, we'll be getting tangents of that curve at different points. Okay, so let's say that we can find, I'm using capital delta. This is small d of y, d of x, but now I want to use delta of y, delta of x. Okay, so because I want to find the slope, we know that these symbols are mainly used when you are finding the slope, like changing y over changing x. There's the definition of gradient, but is analogous to finding the slope. So d of y estimate d of x will be given by, I'm finding the derivative of this. So the first one will be a constant. So this derivative of a constant is 0. Derivative of this term here will be beta 1. And derivative of this will be twice beta 2 estimate, but we have an x there. So this is the slope. The slope of that function, a quadratic linear model, is given by that. And you see, you need to find, for you to get the exact value of the slope, you need to find, you need to be given the values of x. You need to be given values of x. For example, let's consider this model. We have come across this model in our previous classes. So we have this model, log of wage estimate is equal to 1.30 plus 0.046 experience plus, minus 0.000944 experience squared. Then for simplicity, sorry, let me say this faster. Find the effect, or let's say this, explain the effect, explain the effect of experience on the estimated wage. Like that. Okay. Then for simplicity, so solution. No? For simplicity, I want to consider the model in this format. So for simplicity, I'm going to replace those long names with the symbols here. So the estimated log of wage to be represented by Y, then experience to be denoted by S, like that. Then from there, we can find the derivative of this function. And from what we have said there, the derivative of Y with respect to X is given by 0.046 minus 2, 0.000944 of X. So this is the slope of that function. This is the slope of the function, of this function here. That's the slope. And you see, for you to get the actual slope or an exact slope, you need to get the value of X. So the slope that you're going to, or the gradient of this kind of function will be given, or will be at a point, at a given point. The slope can be explained at a given point. It is not general, like in the case of a straight line. So for instance, we want to see the kind of relationship we have between experience and wage. So for instance, we can say in the first year, that is when there's no experience. For someone who has no experience, what is the estimated wage here? Someone who has no experience, that is when X is equal to 0. The number of years of experience is equal to 0. It means that you will have the slope is you can have 0.046 minus 2 times 0.0044, then you put a 0 there. So you have 0.046, which we interpret as 4.6%. And we say that this, you interpret this is the first year increase in wage is about 4.6%. So in the first year of employment, the estimated increase in wage is around 4.6%. So we said that usually you because this is a log level model, so you need to interpret the coefficient in terms of percentage. So in the first year, we have around 4.6% increase in the wage. In the second year, or during the second year, we have the slope is so delta of y, delta of x is 0.046 minus twice 0.00944. Multiply this by 1. In the second year, during the second year of work, this person has 1 year of experience. For someone who has 1 year experience, who has completed 1 year of experience. Now, so here we put 1 here. We put 1 there. Then if you use your calculators to simplify that. So we are saying that during the second year, that is for someone who has 1 year of experience, the change in wage is around 4.4%. So you can do it for someone who is in their third year, or someone who has 2 years of experience. So during the third year, this is for someone, this is when X is equal to 2, someone who has 2 complete years of experience. Then the change in Y, the change in wage, the estimated change in wage is, you can write down the value in percentage form. So for someone who is in their third year of work, that means that the person has 2 years of experience. The change in wage is around 4.2%. So the increment is around 4.2%. Then for someone who is in their fourth year, that is a person who has 3 complete years of experience, and the estimated change in their wage will be around 4%, and so on and so forth. For someone who is in the 11th year, that is someone who has 10 years of experience, then the estimated change in their wage is 2.7%. So you notice that the wage is always increasing. And how do you know it is increasing? Because the coefficient is a positive value. You are getting a decimal value here, which is positive. So that means it's an increase. Is an increase. But it is increasing at a decreasing rate, because during the first year, the change in the wage is 4.6, an increase by 4.6. Then in the second year, the increase is by 4.4, followed by 4.2, followed by 4.0. So it is increasing, is a positive value, but a decreasing rate. So if you are to sketch that, the sketch may not be accurate for this problem, but if you sketch, you will get something like this. It is increasing, but not at the same rate. So if this is the wage, of course, here it can't start from zero. That's a mistake. So it can start from zero. It will start from somewhere, but for the sake of illustration, we can just have it start from zero like that. Then here we have the experience. We find that for people who have just started work, their salary is increasing at a faster rate. But as they get more experience, the salary will always be increasing. Even here it is increasing, but the slope decreases. It increases at a decreasing rate. It increases at a decreasing rate. So basically, that's how you would find the relationship between experience and the wage. So we can say that experience. We note that experience in this case, this is a variable we're calling experience, has a diminishing effect. Has a diminishing effect. Has a diminishing effect on wage. That is, it is increasing at a decreasing rate. It is increasing at a decreasing rate. Then in this scenario, we can also obtain the maximum wage that can be achieved by this person. You see, like this sketch here, you may want to find out what is the maximum salary for this particular person here. What's the maximum wage that can be achieved? So you can also achieve that maximum wage. Maximum wage is also obtained through differentiation. Is achieved at the point, and the point here is experience. At the experience where the first derivative, where the derivative of this function beta naught estimate plus beta 1 estimate of x plus beta 2 estimate of x squared, where the derivative, and this is the first derivative, let me put it like this, where the first derivative of this function is 0. Remember, recall that when the first derivative is equal to 0, we have a turning point. We have a turning point for the given function. And in this case, we may not have a turning point because we expect this being a quadratic function, we know that the slope will be a straight line all the time. But we know that we have a turning point. Yeah, sorry, yeah, we're going to have a turning point. I've noticed that. We're going to have a turning point for this one. We're going to have a maximum value. We are going to have a turning point for the given function. And the turning point is either maximum point, maximum turning point, or minimum turning point, or minimum turning point. Either the highest point or the lowest point. There are various ways of determining whether it's a maximum turning point or it's a minimum turning point using the first order and second order conditions. So what we're going to do, let us find the derivative of this function here. I think we already have it. We said that the derivative is given by delta of y, delta of x is equal to beta 1 plus twice beta 2 estimate of x. So the maximum point is when you equate this to 0. This gives you the maximum point, the maximum change in wage, the maximum wage. Sorry, this will give you the maximum wage. The maximum wage is given by that. Okay, so we can find out the value of x, which will give us the maximum wage. So by just simplifying this, plus twice beta 2 estimate of x is equal to 0, it means that the value of x, you can make x the subject. This is equal to minus beta 1 estimate divided by twice beta 2 estimate. If you make x the subject here, so it means that you take this one to the other side, then you divide by twice beta 2. So this is the value of x that will give us the maximum wage. So this is the value of x. X is our experience that will give us, that will give maximum wage. Yeah, correct. Okay, so let's do that for our example up there. In our example up there, we know that beta 1 estimate is 0.0446. I think I'm using 46. And then the estimate of beta 2 is 0.0030, then 944. So then x is our experience. X is experience. And I can just say that I can just let y to be the weight. So I can say, I don't need this, sorry. So I can say that now the value of x that gives us the maximum wage will be equal to minus. There's a minus in the formula. That formula comes naturally because of a differentiation there. So we have a minus there. Then I have the value of beta naught, beta 1, 0.046 divided by twice the value of, so this value here is a negative. This one has a negative. This one has a negative. This is a negative value multiplied by minus 0.000944. So if I simplify this, you notice that the answer will be a positive number because this will cancel with this. So the answer will be a positive number. And if you work out that, you will get around 24 years. So that means that the wage, the estimated wage will be maximum when experience is around 24 years. I've rounded off that value, so but around 24 years. Around 24 years. So that's the time we expect an individual to have the maximum wage. To have the maximum wage. Okay. Any question there? So next, I want us to look at nonlinear regression, which is caused by having terms which are interacting. Like if you have two variables which are interacting. Let's do that by illustrating, through illustration. Consider the following model. Consider the model, the model below. We have log of the estimate of wage is equal to beta naught estimate plus beta 1 estimate of experience plus beta 2 estimate. Then I have a dummy variable here, female. Then I have a times there. It's just to show interaction. Experience. How am I writing this? Let me write it like this. Expire. Like that. So let me have something like that. So let's consider that model. As you can see here, we have female and experience. Now this symbol here is the one that signifies an interaction. It's not multiplication. But if you want to model the variables female and experience, and you want to include an interaction term, you actually use a multiplication sign. You actually use a multiplication sign to find the multiplicative effect of that. So then we notice that this item here, or this term here, female, that term here is what we are calling, is called an interaction term. It's called an interaction term. It's called an interaction term. We say that this model suggests that the slope, the slope, in this case, experience, the slope effect is different. Is different for males and females. In other words, we do not have the same slope for the two genders. So experience does not affect wage the same way for males and females. That means you have two different lines which have each with a unique slope. Okay. And for you to find that, you again use differentiation. Okay. So we have, for instance, if you take the derivative of log with respect to the derivative of log of wage with respect to experience, then you find that we are getting two slope values for male and for females, as shown below. So when you differentiate this function here with respect to experience, you will end up with this. The derivative of log of wage estimate with respect to experience is going to be beta 1 estimate. So here you get beta 1. And then here, when you differentiate this term with respect to experience, you remain with beta 2 estimate female. Okay. Then we say for the males, that is when female is equal to 0. When female is equal to 0, the slope is given by d log of wage estimate divided by d of experience equal to, if you put 0 here, if you put 0 there, you'll be left with beta 1 estimate. So beta 1 is the slope for the males, is the effect of experience on the wage for the males. Then for the females, that is when female is equal to 1. Remember, these are dummy variables. So now here, instead of putting 0 here, I'll put 1 now. If I put 1 here, so where there is female, I put 1. Then we find that the slope will be given by d log of wage. This should be like that, divided by d of experience is equal to beta 1 estimate plus beta 2 estimate. So the slope for the females is given by this. Is given by this beta 1 plus beta 2. Beta 1 plus beta 2. So that means that if we were to sketch, you will get something like this. Maybe it will look like this. Maybe this is the one for the males and maybe another one for the females. Meaning that beta 2 might be negative in this case. If beta 2 is negative, you'll have it like that. But if beta 2 is positive, you will switch the positions like that. So this is so here you have the experience, and then here you have the estimated wage. So that's the marginal effect of experience on wage. If gender for the two different genders like that. Okay, so that's how you can sketch that to show that the slopes are different. So the slope here, might be, the lines don't have to be parallel. The lines don't have to be parallel, sorry. Yeah, the lines don't have to be parallel, but I think in this case, we can just illustrate using something like that. Okay, so that is it. When you have interaction terms, you end up with something like that. So let's have an example using some actual output. Using an actual output here. So let's consider this model. The estimated log of wage is given by all this. And we say that this model gives, so this model gives the average difference. The average difference in wage for both men and women. For both men and women. Okay, and you're told to do this required. You write down and sketch. Write down and sketch the equations that predict wage for each group, that is women and men. Equation of wage, the equation of predicting wage for men, and also equation of predicting wage for the females. You need to sketch. You'll have something like this. The sketch will be something like this. Will be some 2 lines. Then Roman 2, you obtain the wage difference. Obtain the wage difference for these 2 groups. At 10 years of experience. At 10 years of experience. That is you just estimate the wage for the females when experience is 10 years, and also the estimated wage for the males when experience is 10 years. You take the difference, or you obtain the difference between those 2. And that is basically it for today. That is what we needed to cover today. Any question?